Hello, year 11. So in this video, I'm going to go through a description of the reasons why you should study physics at Haggerston at A level. So I'll just begin by kind of outlining what the course at A level is going to involve, and then explain why Haggerston is good for that course and why you would want to do physics at such a high level. So this picture that you can see here kind of shows a map of physics. And as you can see, physics involves a vast array of concepts that cover things from the structure of space and the universe, to what happens on very small scales, to the way gravity works, and how planes fly, and what temperature actually is. So at GCSE, a lot of what you study is restricted to this region of this map of physics, as they call it, where you think about things like the laws of motion, how light works, and the basics of mechanics and waves. At A level, you get to venture into some of these more exploratory regions of physics. So we touch on quantum physics at A level. We begin to look at dark energy and dark matter and what those mean for the structure of the universe. And we also talk about what heat and temperature refer to and how those concepts are linked to things like energy and kinetic energy. So this overview gives you a sense of what physics means at a high level, and it should give you a kind of guide as to the things that you'll be interacting with as you do physics at progressively higher levels. So I then want to talk about why you would want to study physics. So that broad overview, let's just pin down a few key points about what it will give you if you were to study that subject. So one of the key points is that physics answers some of the most fundamental questions about nature and the universe. So things like, what is time? Did the universe have a beginning? And if so, what happened at the beginning of the universe? What are the smallest pieces of matter? All of those are questions that physics addresses in a really rigorous way. Which brings me on to the second point, which is that studying physics will teach you thinking skills that apply across lots of different spheres of life. So you learn to think about and analyze questions in a very thorough and systematic way. So the rigor physics provides you with not only allows you to answer these really difficult questions, but also prepares you for thinking about lots of different aspects of your own life and lots of different subjects that are not directly related to physics, which then links quite nice to the third point, which is that physics opens many doors. So the subject is well respected as a route into many jobs, including ones that aren't necessarily directly related to physics, many apprenticeships, and many university courses. So even things like economics or finance, which are not directly physics related, are physics A level, and physics understanding is very well respected in those careers and those fields because of the rigor, the systematicity, and the kind of strength of the analysis that you get from studying physics. But obviously, the kind of key thing that you want to think about is what would you actually be looking at in a physics course. So A level, the course spans 2 years, as with most A levels, and there are 6 modules that span those 2 years. So the first 2 modules will look at things like your practical skills, so ensuring that you can effectively plan, analyze, and implement experiments. And the second one will look at the way you analyze data, measure quantities. So things like those basic math skills that apply across all topics in physics are looked at in that second module. The third module focuses on those aspects of classical physics that you'd have touched at GCSE. So how forces and motion interact to create lots of the effects we see. So for example, how forces cause objects to stretch, and how the elasticity of objects has applications in things like construction. You also think about how collisions happen and how we can predict the result of a collision by thinking about the properties of things coming into it. In the fourth module, you look at electricity in a bit more depth and think about how electrical circuits are set up and the principles that underlie our analysis of electricity. We also think about waves. Again, we look at more detail, so some concepts like interference and diffraction that only mentioned at GCSE are then dealt with in quite a lot of detail at A level. And the kind of most interesting bit, the bit that pushes to the boundaries of our understanding, is quantum physics. So you're introduced to the basics of quantum physics at A levels, and it's quite a strange topic. It really undermines a lot of our common sense notions. So we kind of begin to probe a lot of our assumptions about the way the universe works using the ideas of quantum physics in that fourth module. In our second year, you get a chance to look at thermophysics in more detail. Think about how motion in a circle, so whether it's a planet orbiting the sun or a plane flying in a circle as it comes into land, you think about circular motion by applying those laws of physics that you'd have learned in the first year. You also think of oscillations, which might seem like a kind of one interesting topic that is marginal, but oscillations determine things like the way a car comes to rest after traveling over a bumpy bit of road. It also deals with lots of really key aspects about how things like battery charges work and the way circuits behave. So oscillations actually applies over a wide range of topics. You also look at gravitational fields. So we take our scope and start looking at scales as large as the solar system and galaxies and thinking about how gravitation causes stars to come together and how we can think about the laws of gravitation to explain the motion of objects in the solar system in really rigorous detail. And the final bit of Module 5 is about astrophysics and cosmology. So in this topic, we think about the origin of the universe, its evolution, and what its potential end might look like. We also think about the evidence that we can gather to interpret the behavior of stars or to predict how the sun, for example, might die eventually, to predict how galaxies interact when they collide. So how we can use information from very distant objects to actually make really rigorous and robust conclusions is the focus of the astrophysics and cosmology topic. In Module 6, you then get to look at capacitors, electric fields, and electromagnetism. And those three topics kind of come together to build on what you have done in electric circuits to then more robustly describe how we can use the behavior of charged objects like electrons, protons, nuclei to have some really interesting effects. So things like the way a generator works, the way motors work, the way that electric fields actually keep the atom together are kind of really probed in that topic. You then look at nuclear and particle physics. So again, this pushes to the edge of our understanding. We learn about what's called the standard model of particle physics. So what are the small particles that make up everything? How do we know about these small particles? And if we were to zoom into the atom, what would that look like? Which is something you think about at GCSE, but we go further than that. If you were to zoom into the nucleus, what would that look like? If you were to zoom into the proton and the neutron, what's actually inside of those particles that wasn't discussed in previous levels of education? You start thinking about what makes up a proton, what makes up a neutron, and how do they stay in the nucleus together? And finally, you think about medical imaging. So it brings together lots of these different topics, things on waves, electromagnetism, radiation, oscillations all come together to think about how we can apply these concepts to both understanding the internal workings of the body, but also to treating some diseases in ways that are not invasive, so that don't require you to cut open someone or do these quite potentially harmful processes. So it's kind of a nice way of concluding the course by thinking about how all of these applications can save people's lives and improve the actual experience of humanity. So that's an overview of the course. And I want to just focus on a few points within the course that I think are of particular interest and that can motivate you to study the subject. So one of the things we look at is something called electron diffraction. So at A-level, you have a chance to think about the way that electrons, which you discuss over and over again in the context of electric circuits, but also in chemistry and chemical bonding, can behave like a particle or a wave. And it's a really interesting experiment that we look at where if electrons are fired at a sheet of graphite, they exhibit a wave-like property that allows us to then treat them as waves. So you learn about this thing called wave-particle duality, where objects that seem like a solid sphere, like a kind of object that you can touch and hold, actually behaves more like a wave. So this kind of diffuse thing that passes by you and causes these effects that are less structured and deterministic. The next thing we look at is the kind of life cycle of the universe. So how the universe begins at the Big Bang, what happens in those first few seconds after the Big Bang to kind of set the pace for the rest of the universe's existence, and how in the first few hundreds of thousands of years the universe gains its basic structure and gradually evolves. So at A-level, we discuss this diagram and make a lot of sense about the evolution of planets, galaxies, nebulae, and stellar structures, and how all of those things can be described through the laws of physics, and how by looking at our current universe, we can make really interesting deductions about the way the universe would have started. On the topic of medical physics, we also talk about ultrasounds and how we can link our knowledge of oscillations, electricity, and waves to discuss how ultrasounds are both created, but also we can interpret the information that comes from them. So that gives us a really good understanding of the way that physics is used in these medical applications, that we are aware of their presence, but we don't know very much about how they work until we do these topics of A-level physics. Another really interesting thing that we look at is the way that these things, this is a particle collider, are used to probe the inner workings of the smallest particles that we know. So we discuss how the proton, the neutron, and the electron are investigated by accelerating them to very high speeds and colliding them at very high energies and observing the things that propagate from it. So we get a chance to really think about, how do we actually investigate these very small particles? What does it look like if these things were to collide with each other? And what can we deduce about the particles based on their behavior under these extreme conditions? So this is kind of an overview of these key topics, which gives you a sense of why physics as a subject is interesting. The next question to answer, obviously, is why should you do physics at Haggerston in particular? So one of the obvious motivations is that the results that we get are very strong. So over the course of the last 4 years, we've averaged a position in the top 10% of schools. In 2 of those 4 years, we're in the top 2 to 5%. So among the best schools in the country for the progress that students make from GCSE to A level. And the average grade across the last 4 years was a B. So students come in obviously with a range of grades, so 6 and above generally, and they get at least a B on average after they pass through Haggerston's 2-year physics course. So with the average grade of a B, there's obviously also some very high achievers. So there's some real success stories that we celebrate. And I contacted some of the former students recently, and some students are now studying medicine at UCL. Others are working as an engineer in the City of London. Someone else is studying physics at Cambridge. Someone else is doing architecture at UCL. So you can see that people do a variety of things from the course. It doesn't just set you up to do a physics degree, although some people do that. It can also prepare you for something a bit less related, like medicine and architecture, or something a bit more practically applicable, like engineering. The other kind of big motivation is that at Haggerston, we work to bring the subject alive. So last year, we took our year 12 and 13 students to the largest physics lab in the world at CERN in Switzerland, which gave them an opportunity to see the practical applications of the subject. So lots of things that they learned about in lessons came alive during that trip, and they were able to both see physics at its most advanced stage, but also to see a different culture in a different city and get a kind of, experience of what it's like to travel to different parts of Europe. So it both informed their physics education, but also their wider growth as students to kind of understand this separate culture while also learning lots of physics at the same time. So something to just kind of reiterate and make clear is that the subject is very mathematical at A level, and so we require both a grade 6 in physics and in maths. You can also get a grade 6 in combined science. So we're just looking for a 6 either in physics if you're doing separate, or in combined science if you're doing combined, and a 6 in maths as well. And I've just indicated here some of the kind of key concepts that are introduced at A level to show you the level of mathematical rigor that we require. So we've got Newton's law of gravitation, which requires a really robust understanding of inverse square law, so understanding how the force varies with the inverse of the square of the distance, which means you need to be really comfortable with those things, the algebra surrounding that. We also have the graphs showing how temperature and velocity are affected for different samples of particles. You need to be really confident analyzing graphs and interpreting data in these forms. And we also look at lots of rates of change. So you need to be confident with a new concept of rates of change that comes up, which requires you to be able to use abstract maths and apply it to these physical contexts with a lot of confidence. So that kind of sums up the motivation for physics as a course, the motivation for Haggerston as your choice to study that course, but also the requirements for physics to give you some motivation as to why you'd want to excel at your GCSEs to prepare you for this kind of subject that will open these doors and provide these opportunities for you. So I hope you choose this subject in this course if there are things that are well suited to your abilities. Thank you.